Okay, we will go ahead and finish up chapter 22 here, looking at what are called oxidation reductions of aldehydes. There are two, the Tollens and the Benedict's test. There are videos for these, or there will be videos in the folder for this lecture, but these oxidations are specifically for aldehydes. They will not react with anything else. So for instance, if we take our aldehyde and we want to oxidize it using what's called the Tollens reagent, the Tollens reagent is a mixture of silver, iron, ammonia, and hydroxide. And that will undergo oxidation to form the carboxylic acid. Now, because the solution is basic, the carboxylic acid will be deprotonated. So initially you make the carboxylate, the deprotonated carboxylic acid. This is an oxidation reaction, so the aldehyde's being oxidized. That means that the silver is being reduced in this process. And so if we look at that, what we are, remember that oxidation basically means you lose electrons and you gain electrons in the reduction. So that means the silver plus ion goes to silver metal. And then the ammonia and the hydroxide are just there for the reagent. So this test can be used to determine whether or not you have an aldehyde. It can also be used to make what is called a silver mirror. So if you look down here and on the video, the first is just the, this is a solution of basically of a sugar. So if you had, for instance, you could use dextrose for this. You have the open chain form of the sugar with all of the OH groups. I probably haven't put enough in, but you get the idea. So in the open chain form of that sugar, there's a free aldehyde. And you can go back and look at the previous lecture for all the structures of the sugars. If we treat that with our silver ion and our ammonia and hydroxide, what happens is the solution initially darkens, and then what you see is you see this silver mirror form on the inside of the test tube. So you can think of this, let's say we're basically like making a ornament out of the test tube, or silvering the inside. And this is the way that silver mirrors used to be made on glass. Now they're probably just, it's probably a molten tin kind of a compound, but this is actually the old way that silver was added to mirrors. So if you have older mirrors, you might see this kind of discoloration because basically the silver metal is tarnishing. Then my summer class, we got into this whole discussion about vampires and werewolves and why silver, just to sort of make it to cut to the chase, in the vampires can't see themselves in mirrors. Why is that? Well, there's something special about silver in relationship to all these supernatural beings like vampires, and so they couldn't see themselves in the mirror because the mirror was made of silver, because that's the way they silvered the mirror in the old days. And we've used this to like silver round bottom flasks and Erlenmeyer flasks. So it's a relatively straightforward process. But that's what you would see as part of that reaction. The thing is, this is specific. So this reagent only reacts with aldehydes. It won't react with alcohols, double bonds. It only reacts with aldehydes. So you could, for instance, say, well, if I had, for instance, a secondary alcohol and I had an aldehyde in my same molecule, and I wanted to oxidize the aldehyde, what I could do is I could treat that with the silver metal ammonia and hydroxide, and it would only oxidize the aldehyde. So the secondary alcohol would be intact. Once we do this reaction and we form the carboxylate, because this is basic, we would then want to add H+, and we would be able to convert our molecule back to the carboxylic acid. So this is a very specific reagent that will only oxidize aldehydes. And it also has this visual test that can be used to determine if something has an aldehyde, is an aldehyde or has an aldehyde in it. Again, using a sugar is most straightforward because even if there's a small amount of open-chained aldehyde, it will react with the silver. The second of these specific oxidations for aldehydes is the Benedict's test. And so the Benedict's test is also very specific. And you may have used the Benedict's test in biology to look at what's called a reducing sugar. So the reagent is we react our aldehyde with copper-2, iron, and hydroxide. Again, the aldehyde is oxidized, the copper is reduced. So that means the copper gains an electron. So again, this is in basic solution. And so what happens is we oxidize the aldehyde to the carboxylic acid, but it is deprotonated because it's in basic solution. And then the copper gets reduced down to copper 1, which then combines with oxygen to form copper. This is copper 1 oxide. And again, this is in basic solution, so you form the deprotonated carboxylic acid. If you then added H+ to that, you would form the carboxylic acid. So this is specific for an aldehyde. What is this in this diagram down here? It shows you the reaction itself. Copper, remember that copper 2+ ion is blue. And if you've in general chem, you've seen that. This can actually be used to test food to see if it has some reducing sugars in it. What is a reducing sugar? Basically, a reducing sugar is not something like sucrose. So if you think about our structure of sucrose, we've got, in essence, a 6-membered ring and a 5-membered ring that are held together. That would be sort of a generic structure of sucrose, and you can look at that exact structure in the last lecture. But this is an example of not a reducing sugar. So if you just had if you had fructose, fructose will not react because it's made from a ketone. But on the other hand, if you had dextrose, basically that means that the dextrose would be in its 6-membered ring. And remember that this, in its open chain form, would have an aldehyde, a free aldehyde, along with the CH2OH group. So that's an equilibrium. So there is a small amount of that open chain form, but it would have the aldehyde to react. So this can be used to test for foods to determine how much of the basically free dextrose is present as opposed to what is sucrose. And so this brick red precipitate is the copper 2 oxide. And the reason that it's brick red is because that is the pigment that's used to make bricks red. So you can actually do testing on this to determine how much of the reducing sugar, how much of the dextrose, for instance, is present in solution. Again, this is a very specific reagent for aldehydes. It will not react with alcohols. It will only oxidize aldehydes. And there's videos in the folder for both the Tollens test as well as the Benedict's test. So those are specific oxidations that we have for aldehydes. Now, the next compound that we can make out of an aldehyde or a ketone are by a mechanism called addition-elimination. So first of all, we have to define what a primary and a secondary amine are. And we should take a step back and just kind of think about, what have we done with aldehydes and ketones? We've added water and we've added alcohols. Now let's go ahead and add an amine. What kind of amine? Well, primary and secondary amines are based on how many alkyl groups are attached to the nitrogen. 1 primary, 2 secondary. They will give 2 different products with a double bond in 2 different positions. So if you react a primary amine, and we'll go through the mechanism of this in a moment, if you react a primary amine with a ketone, you end up adding, or you end up replacing the oxygen with the NR group, and notice the 2 hydrogens are gone. That's because the other product that you form is water. This is called an imine, or what is also called a Schiff base. Technically, an imine is when you add ammonia so that you form an NH up here in the carbons double bonded to an NH. That is an amine. If the nitrogen has an R group on it, then technically that's a Schiff base, although most people use these terms interchangeably. So we'll talk about the mechanism for that in a moment. What happens if you're in a secondary amine? If you react a secondary amine with these aldehydes and ketones, then what you end up with forming is what's called an enamine, and the enamine would have the carbon, would have a carbon-carbon bond here. And this is going to be a different R group, so we'll go through this mechanism. Let me put a prime over here because basically that's the R prime. We'll go through that, but notice the double bond is in a different position. And so we'll go through the mechanism of the forming the enamine. So depending on whether it's primary or secondary, you'll get either an imine or a Schiff base, or if it's secondary, you'll get an enamine. So let's work through the mechanism of this reaction. Well, before we do that, I guess I'm going to go off on a little bit of a tangent here, although it's not much, on different types of amines that you will see in the textbook. And basically, I have to correct these because for some reason they didn't transfer over. There. There is a whole area of what are called qualitative analyses. And what a qualitative analysis test is, it's something that's a visual test for a functional group. Now, at this point in the semester, going through Organic 1 and on the tail end of Organic 2 here, we've talked about spectroscopy in the lab and how you can determine structures. Well, how did people determine structures of molecules before they had IR and NMR and mass spec? They had to do all these visual chemical tests. And so the visual chemical tests they did were this qualitative analysis. So when I was an undergrad, back in the mid to mid 80s, our second semester of organic, we had the entire second semester, we were handed 4 test tubes and we had to figure out what the compound was. We had limited access to an NMR. We did have an IR if you knew how to use it. We had no mass spec. So how did we determine the structure? Well, first thing we had to do was figure out what the functional group was. So there's lots of visual tests that we've already talked about. We just haven't focused on the color changes that you would see. For instance, bromine is an orange liquid. If I suspected that my molecule had a double bond, I would add a drop of bromine to it, and if the orange color immediately disappeared, it's the bromine reacted with a double or a triple bond. In free radical halogenation, it takes quite a while for that bromine to dissipate, but it reacts rapidly with a double bond or a triple bond. We can also think about KMNO4. Think of what you did in the lab. KMNO4 is a purple solution. When it oxidizes something, it forms MnO2, which is the brown precipitate that we saw in our lab when we did part B of the benzocaine synthesis. So if you think you have a functional group in there that will react, you could add a drop of KMNO4 to it, and if you immediately see the purple color disappear, but a brown precipitate forms, something in there oxidized. Maybe it was a double bond that got cleaved or 2 OH groups added. Maybe it was an aldehyde that immediately got oxidized. So these are examples of qualitative analysis tests. The importance of these forming amines and Schiff bases are that some of the reagents that we use are very reactive with aldehydes and ketones. So if you can imagine that I have narrowed down my functional group to whether or not I have a ketone or an aldehyde versus a carboxylic acid and all the derivatives that we'll talk about in the future, if you added a drop of any one of these primary amines, what you would end up with is you would end up with a reaction. And so all of these compounds, if it's a primary amine, you could make an imine, or using hydroxylamine, you could make an oxime. The one that's used the most is 2,4-dinitrophenylhydrazine. This has a color to it. If you had an aldehyde or ketone and you added this 2,4-dinitrophenylhydrazine, which is also called 2,4-DNP, what would happen is it would immediately react and you would have a precipitate formed. That precipitate would be any color from orange to red-orange to yellow. There's a whole variety of colors that you can get. But the idea is that the 2,4-DNP reagent forms this Schiff base that then precipitates from solution, and because of the nitro groups that are added to benzene ring, it has a vibrant color. So if you had a carbonyl group, you'd say, well, what kind of carbonyl group do I have? You'd add a drop of 2,4-DNP. If you got a precipitate, then you would know that it's an aldehyde or a ketone because none of the other carbonyl groups react with that reagent. It would go so far as you would collect that precipitate, you would purify it, you would take a melting point, and there are books where people have taken known ketones and aldehydes. They've prepared this 2,4-dinitrophenylhydrazone compound, measured the melting point, so you could measure the melting point, and by comparing this precipitate's melting point, you could actually work backwards and say, oh, that's the ketone that I have. You can do the same thing with a semicarbazide, making a semicarbazone. So these are used in qualitative analysis. As I said, when I was an undergrad, we spent half of the semester trying to determine what our 4 unknowns were. Half the time the reactions didn't work. We were getting the keys and going into the lab, more than just 4 hours a week trying to figure these things out. It was close to a research experience as I had as an undergraduate, and so it was frustrating at times, but there was kind of a logic to it. And we don't do this as much anymore, simply because we have spectroscopy that can help us identify these molecules in less time with less chemical waste. So that's kind of a sidetrack of the importance of forming these Schiff bases in qualitative analysis. But let's talk about the formation of the amine. So let me take a ketone, and I'm going to go ahead and put an R group there, and I'm going to react it with a primary amine. We'll call that R2. Now, the first thing is, when we reacted a ketone or an aldehyde with acid, when we reacted an aldehyde or a ketone with water or alcohol, we needed an acid. I don't need an acid here. As a matter of fact, if I added H plus to this reaction, the nitrogen would react with it, and I would form an ammonium ion, which is no longer a nucleophile, that will add to the carbonyl. So we don't add acid to the mixture. If we remember from our periodic table, as you go from right to left on the periodic table, you form a stronger base. You also form then a stronger nucleophile. So nitrogen is a stronger nucleophile than oxygen. So I needed acid when I reacted my aldehyde and ketone with water or alcohol. I don't need the acid here because, number one, it'll screw up the reaction, and number two, nitrogen is a strong enough nucleophile. So the nitrogen is going to come over and directly attach and attack the carbonyl. So I'm going to end up with an O minus along with the whole amine group is going to add. So I'm going to end up with what is, I guess in the older terms, called a zwitterion. So zwitterion just is one that has a positive and negative in the same molecule. Now that's not going to be very stable, and the O minus is going to want to take away the proton from the nitrogen. Whether that happens intramolecularly or whether two of these molecules collide and the N and the H plus is taken from the N by another O minus is kind of irrelevant. I'm just going to write the sort of arrow here as if it happens intramolecularly. It probably doesn't, but what I'm going to end up forming is I'm going to end up forming then the neutral molecule with an OH and an NH group. Now you may say, is this a hemi something? Actually it is, but the textbooks don't talk about this. This is called a hemi-aminal. And the only reason that I know that is because we were trying to synthesize a Schiff base in a project many years ago, and we ended up forming the hemi-aminal as our product. And I'm like, wow, I don't even know what the name of that is. So then I looked it up, and sure enough, it's a hemi-aminal. Now, what will happen in this case is this reaction occurs under heat. And so the next step I'm going to show you is like, wait, does that really happen? Under heat, we're going to say it does. So when I heat this molecule in the reaction, what's going to happen is we're going to move this pair of electrons from the nitrogen, the water's going to leave, and we're going to end up then with the double bond to the nitrogen, and we're going to end up with H2O. And so that's how we're going to form our amine or our Schiff base. So I know that step isn't necessarily the most appealing, and maybe this reaction actually occurs by two molecules where the OH grabs the nitrogen and creates that process, but this is how we can simplify that reaction. Now, all of these are equilibrium steps. So this is an equilibrium reaction. The reactions that I showed you earlier, I'm just going to go back for a moment. All of these reactions actually form every single one of these compounds, because when they precipitate from solution, that pushes the equilibrium by removing product, which basically is a Le Chatelier principle to push the equilibrium to the right. So we can push the equilibrium to the right by either forming a solid as our Schiff base, or you could also push the equilibrium to the right by removing the water as it's formed. And so if you're going to make an amine or Schiff base, that's typically what you do. So this is the mechanism for forming the amine or the Schiff base. Okay. Now, what happens when we react the secondary amine and we form our what we call enamine? Well, let's look at that mechanism. So I'm going to do the same reaction here, except now I'm going to react with, and I'm just going to use two R2 groups here, with now a secondary amine. Again, no acid is needed because the nitrogen is strong enough as a nucleophile. Acid will just turn the nitrogen into an electrophile having a positive charge. So we don't want to use acid. The nitrogen will come in, and we'll do the same first step that we did before, and now we'll go ahead and put in our equilibrium arrows. We'll form our zwitterion. With our nitrogen having a positive charge, and then the O- will grab the proton, so that we'll form our hemi-MnO in this case. Now, here's the problem. In the previous reaction, there was a hydrogen attached to this nitrogen that could be lost with the OH to form the double bond. In this case, there's no hydrogen to lose. So let's do this reaction with a real compound to see what happens. So how about I take cyclohexane and react it with what I'm going to call dimethylamine. So the nitrogen comes in, attacks the carbonyl. I end up with my O-. My plus charge on the nitrogen. My O- will then, we'll say, intramolecularly pull off the H+. And now I'm going to form my hemi-MnO. Now, in the presence of heat, we're still going to lose the OH group. But since this nitrogen has no hydrogen to lose, what happens is one of the hydrogens that is on the carbon next to what was the carbonyl, so if I write in the original molecule, that hydrogen is going to be lost. So under the presence of the heat, I'm going to lose that H and OH, so I'm going to form water, and now I'm going to form the double bond to the carbon that was next to the carbonyl group in the original molecule. So that's how I form my enamine. Okay. And again, this is an equilibrium process, so best case scenario is we could remove the water in order to form enamines and push the equilibrium to the right. But the double bond is formed between the carbon that is attached to the carbonyl and the carbon that was the carbonyl to begin with, because the nitrogen is secondary, and so there's no hydrogen after it loses its initial hydrogen to the O-. Now, this could set up a situation where you might say, well, what if the two carbons are unsymmetrical? So let's say I have this cyclohexane and I react it with diethylamine. I could form two different products here. I could first form the double bond to the carbon with the methyl group. Or I could form the double bond to the other side. Well, we now have two products. Which one is the major product? What if I said that the major product was the more stable one? Which one would you say is the major product? If the major product is the more stable product, the double bond is more stable in this case, and so that would be the major product of that reaction. Okay. All right, so when we add nitrogen compounds, we're either going to add primary or secondary, and we're going to form either a Schiff base imine or we're going to form an enamine. And these are the mechanisms which you'll have to draw out in the future. Okay, another reaction of aldehydes and ketones is a fairly important one. It is called the Wittig reaction. In German, W is a V sound. I believe it's George with no E on the end of it, Wittig. And this reaction allows us to take a carbon-oxygen double bond and form a carbon-carbon double bond out of it. And in forming the carbon-carbon double bond, we end up being able to add a whole chunk of what originally was an alkyl halide to that carbonyl group to make a double bond. So the Wittig reaction is important. George Wittig won the Nobel Prize because it's forming a carbon-carbon bond and a carbon-carbon double bond at that. And I've talked about this sort of in passing, the idea that in modern synthesis, if we had some big molecule that was maybe had a double bond in it, what we might decide to do is to prepare half the molecule as a ketone, the other half is what I'll show you as an alkyl halide, and then when the two big molecules are made, we could couple them together using a Wittig reaction, kind of like how we coupled with Suzuki coupling or with Heck coupling or even with Gilman for that matter. So Wittig is an important reaction from that standpoint. So how do we do this reaction? Well, the first thing we do is we have to correct this. And we got a carbon here. So let me go through the mechanism of how this reaction works. So I'm going to give you the sort of the mechanism here. The first thing we have to prepare is, let me go back. The first thing we have to prepare is what is called the ylide. The ylide is what I'm going to react the ketone with. And notice the ylide has a phosphorus plus with a C minus. You might say, why don't you just form the double bond? Okay, we'll do that. But this phosphorus is triphenyl phosphorus that we talked about in Suzuki. No, we talked about that in Heck coupling. And I'll show you how this works. So ultimately, we're going to make the ylide from an alkyl halide. It can only be primary or a secondary alkyl halide. Of course, this AB group is what I'm going to attach up here. This AB group is what I'm going to attach up there. And if it had 3 alkyl groups on it, that would be impossible to form the double bond. So it's only a primary or secondary halide. So how do we do that reaction? The first thing we do to prepare the ylide is we take our alkyl halide that has 2 R groups and a bromine, let's say. And I'm going to react that with triphenyl phosphorus. Now, on the periodic table, we got CNOF. P is under nitrogen, so going down the periodic table means that it's more nucleophilic or a stronger nucleophile. So phosphorus is a stronger nucleophile than nitrogen. The phosphorus will come in, attack this carbon, kick off the bromine. I'm going to do an SN2 reaction. So my triphenyl and the phenyl group is equal just to a benzene ring. So triphenyl phosphorus is this, with 3 benzene rings attached to the phenyl. So my phosphorus comes in, adds to the carbon. There is a hydrogen. There is an R group. There is another R group. The phosphorus picks up the plus charge. Where does the bromine go? The bromine is just kind of hanging out as a Br minus, but the way we write this is we write the Br minus being the counter ion to the P plus. Okay, so we have our initial molecule. Then what happens is this is not the ylide. The ylide is if you take an organolithium compound as a strong base. So we take a strong base like an organolithium compound, that R minus comes in and deprotonates the hydrogen. So now I end up with the phosphorus with its plus charge attached to the carbon with its minus charge. And now we have the 2 R's and the organolithium compound was deprotonated. The specific organolithium compound that is used most times is what is called butyl lithium. And I've done a lot of work with butyl lithium in terms of looking at structure, so it's something I'm very familiar with. It basically is used in this case as a strong base to deprotonate that carbon to make what is now called the ylide. So then what happens with the ylide is it's going to react with the carbonyl. So let's take a step back here. So what happens is I'm going to keep the phosphorus with a plus charge and the C with its negative charge. So if we draw the arrows this way, what happens is the C minus will attack the carbon, and then this pair of electrons from this double bond from the oxygen will come over and add to the phosphorus. So what we end up doing is we end up forming this carbon-carbon bond and this phosphorus-oxygen bond. And this is what is called a oxaphosphetane. You don't have to know all these names, but this is what is called an oxaphosphetane. In the older literature, it was called a betaine. So we make this four-membered ring. Now, I mean, we've made four-membered rings in the past. How about a little review here? We have a double bond. We add a boron to it. Right? We had something like this. And we ended up adding the hydrogen and the boron, anti-Markovnikov, 100% cis. So this is nothing new. We're just forming this oxaphosphetane betaine, and then in this process, that four-membered ring is going to cleave. So I'm going to take this pair of electrons in the phosphorus carbon bond to form the double bond, break the CO bond, and what I end up doing is now I end up forming my carbon-carbon double bond, and I also end up forming what is called triphenyl phosphine oxide. And the PO double bond is very stable, so that's why that reaction works. So you wouldn't need to write this mechanism, but I'm kind of showing you how the Wittig reaction works. So if we go back and just step back for a minute, what do? I take my alkyl halide, I treat it with triphenylphosphine. I end up forming, this is molecule B, I end up forming the phosphorus carbon bond. The bromine is over here as my negative, and then I take that and I take that hydrogen and I use N-butyl lithium. That's the same molecule that I wrote before, and now that deprotonates this hydrogen to then form, and the bromine at this point is gone. That forms my ylide. Okay. So what would be an example of a Wittig reaction? Well, let's say that I had a cyclohexanone and I wanted to add to that, how about I just do this? I want to add to it another cyclohexane ring. So what I would say is, well, I'll start with this alkyl halide. I'm going to treat this with, number one, triphenyl phosphine. Number two, I'm going to treat it with butyl lithium. And then that molecule is going to couple together so that what I'm going to end up doing is I'm going to end up replacing this oxygen with this entire alkyl group. So I could end up coupling those two benzene, or those two cyclohexane rings in a double bond. So you can imagine this would be kind of complicated if there were a lot of groups over here and a lot of groups over there. I could prepare those two molecules and then use the Wittig to couple it together. So a Wittig reaction is important from that standpoint, that it allows you to take the ketone or the aldehyde, either one, and then react it with an alkyl halide to couple these two carbons together through a double bond. Okay. Now, I'm going to throw in the following reaction, which is what is called Baeyer-Villiger oxidation. And this is actually a very important reaction to form cyclic esters. All right, so this reagent is messed up. Here is the reaction. What I'm going to do is I'm going to react a ketone, and this is only for a ketone. I'm going to react it with our friend, the peroxy acid. And what's going to happen is I'm going to insert an oxygen in between the carbonyl and one of the two alkyl groups. And I'm going to make an ester. Where will the oxygen insert? It'll insert on the side which has the larger alkyl group attached. And so this is called Baeyer-Villiger oxidation. We're not going to get into the mechanism of this other than we're going to insert an oxygen between the carbon and the alkyl group. So if I took something like this ketone, and I said I'm going to react that with a peroxy acid, I would end up easily forming that ester. And notice there's 1, 2, 3, 4, 1, 2, 3, 4. So I didn't lose any carbons along the way. Now, what's really important about this reaction is, and I'll just, it is a great reaction to form a cyclic ester. So let's say we started with cyclohexanone. If I was with cyclohexanone, I treated that with a peroxy acid. What I will end up doing is inserting the oxygen into the ring, and I'll end up forming a 7-membered ring. Probably the easiest thing to do would be to say, well, let's start with a 5-membered ring, treat it with a peroxy acid, and I'll end up forming the 6-membered cyclic ester. Cyclic esters are called lactones. And lactones are very important compounds to make synthetically. If you could imagine trying to make a lactone by something like a Fischer esterification, you would have to have like the OH group on that side of the molecule, the carboxylic acid group on that side. You would have to say, well, I'm going to treat that with acid and heat. I'm going to try and do a Fischer esterification. And you would have to hope that this O group would come and react intramolecularly. And you can imagine that, remember, there's a billion of these molecules in the solution. So what's the chance of forming the intramolecular reaction between the alcohol end of one molecule reacting with the carboxylic end of another one, forming some long chain? So the idea of Baeyer-Villiger is it lets you start with a ring and insert an oxygen within that ring. So it's important from the standpoint of forming lactones that way. You would get, down here, you would get just a mixture of products. Some of which might be the lactone, but others would be these long chains polyesters, which we'll talk about in the next chapter or so. Okay, so this is that is Baeyer-Villiger oxidation, and it is useful for forming those cyclic esters. No mechanism for that, that's just what happens. But again, the oxygen is going to be inserted on the side with the larger group attached. All right, just a couple things. Reductions of aldehydes and ketones. If you have an aldehyde or a ketone and you treat it with either lithium aluminum hydride or sodium borohydride, when you reduce them, you're going to end up with the alcohol. If you want to completely reduce the carbonyl group to a CH2 group, what reagent do you need to use? Wolff-Kishner or Clemenson. So there's a couple ways that we can reduce aldehydes and ketones. One to form an alcohol, one to form the CH2 group. And those are both review reactions that we have talked about. Conjugate addition. To kind of end this, to end the chapter. We're going to talk much more about this in the future. As a matter of fact, you know what? We're going to talk about this in the future, so I think at this point we're going to postpone. We're going to postpone this until chapter 26. So, if there's any problems, 22.5.11, you don't have to do those problems. So that way, we'll talk about that in the future. Okay. So that ends the lecture. There will be a online quiz, or actually there might be 2 online quizzes for you to do as part of this, which will be due at midnight of the next lecture period. Okay. If you have questions, bring them to the Zoom lecture or Zoom question and answer session, or also you can put them on Piazza or email me directly. Okay.